Hi everyone, my name is Samuel Diaz Hernandez. This is my experiment 2 from physical experimentation and statistical thinking. In this experiment, we will estimate experimentally the value of G, that is gravity, with linear regression techniques and the method of the least squares in the emptying of the Maria tank for the constant flow regime. Right here, we have our theoretical velocity out, that is 1.36, with our experimental velocity out is 1.32 with a percentage standard deviation that is 51%. In experiment 1, we mentioned the laws that are used for the experiment. So right now we are going to check the importance of the experiment to check the established value of G, that is gravity. In the theory for this experiment, we have the equation for gravity, that is G, that is the gravitational constant, that is 6.6743 per 10 at minus 11, the m, that is the mass, and the radius square. Also, we need the micro. Also, we need to know what is a microfluid. Right here, you can see what is the microfluid. For our equipment and materials, we have the marriott bottle that was built and used in experiment 1, a chronometer, a ruler, tape measurement of flexometer, and 3 liters of water. Right here we have our experimental setup. Identify as well the cross-sectional areas to be determined. The R out is the area of the drain tube, determined by the diameter, that is this one. A in is the cross-sectional area of the bottle, determined by the diameter, that is this one. A tube is the cross-sectional area of the central tube, that is this one, right here. And the AH, that is the area of the water-free surface. This is equal to A in minus A tube. Right here we have our experiment and our experimental data. Our experimental analysis, we have the same battle of Mariota figure 1, but we have the BH that in this experiment is the same as the B in that we do in experiment 1. Also, we have right here the HT that we can calculate it by BH per T plus H0. For this experiment, we are going to do exactly the same as we did in experiment 1. But in this case, we are going to change the value of H 5 times. And we are just going to use the measurements when the water is into the tube. So when the level of the water is below the tube, we are going to stop doing the measurements. So right here we have 5 experiments with different value of H. Right here we have our table 2.1, that is the measurement with H in 9.50, and his table with the line obtained by least squares. Right here we have a table 2.2 with H equal to 3. As we can see right here, if H is less, we are going to have more data to work right here, as you can see. So we have our table 2.2 and his table, the table 2.3, that H is equal to 4, and his table. Right here we have our table 2.4 with H equal to 5, and his table. At least we have our table 2.5 that H is equal to 6, and its graph and his graph. Right here we have our measurements of H that we do with the velocity h. Right here we have our velocity h that have a 3% standard deviation, and right here we have the BH square with the 9% standard deviation. Right here we have his table. The value of the slope in the line in the figure 4 will be equal to the constant c of the following equation. Okay, so right here, p that is equal to 0.005222 will be c that is in this equation. So right here in table 4 we have the value of c that we already see it with their standard deviation, and we have g with its standard deviation, that g with our experimental result is 7.06. In this experiment, the accepted value for g is 9.81. So as we can see right here, we do not have the value even in the uncertainty, and this is because we do not do a lot of repetition of the same experiment. So it was a little bit difficult to have the measurements correct. So right here, my conclusion, the percentage of my uncertainty for G is 12%, but also with this uncertainty that it's a little bit high, we are not even in the accepted values for the experiment. So in this case, it's just that we have some error of measurement because we do not have a perfect time to stop the chronometer. So as we just did it once, we do not have a very good measurement. So in this case, what we can do to improve this experiment to do it better is to make a lot of times the same experiment with the same value of h. Thank you.